Howdy class. So I briefly mentioned this in the last video, and we worked with the noble gas notation a little bit in class on Friday, but here's another description of it. So once we get above Z equals 10, so once we're past neon, typically most people don't write noble gas notation for helium plus atoms. They wait until they get to neon. But your book basically just says when we get to such long electron configurations that we don't want to write them anymore, basically, we represent those electron configurations in noble gas notation. So noble gas notation means we have core electrons as the most recent noble gas. So for calcium, for example, the most recent noble gas was argon. Calcium is number 20 on the periodic table, and argon is number 18. So it's the most recent noble gas. So we have these electrons, these core electrons, are the electron configuration for argon. So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, we just write argon in brackets as our noble gas core. And then the remaining two electrons are in the 4s2, the 4s orbital, so we just write them by themselves as 4s2. So the noble gas notation for calcium is argon 4s2. And let's talk about this notation a little bit more. So argon is the noble gas core, and the outermost occupied subshells are called valence electrons. So the 4s2 electrons for calcium are calcium's 2 valence electrons. Calcium has 2 valence electrons. And those are going to be very important for us in the next chapter and the following chapters when we start talking about bonding in our elements. All right, so let's practice a little bit. What is the electron configuration for radium? Radium is number 88, discovered by Marie Curie. So she's like the most famous woman in chemistry, won both a chemistry and physics Nobel Prize. So she's pretty cool. And she discovered radium and radiation in general, which is probably what killed her. But let's look at the electron configuration for radium anyway. So we've got 88 electrons to put into different orbitals. So I'm going to draw my diagram again. 1s, 2s, 3s, 4s, 5s, 6s. Let's see if that's enough. It might be 2p, 3p, 4p, 5p, 6p, and 3d, 4d, 5d, 6d. I don't know if I need all of these. Then 4f, 5f, 6f. All right, so 1s goes first, then 2s, then 2p and 3s, 3p and 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, and then 7s will be down here. Let's see if we need that many. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, and then my next one is 4s2. Okay, now, so here, 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 here. Now we're on the next one, so 3d, so d's get 10, 3d10, 4p6, 5s2. How many electrons do we have so far? So 1s2, 2s2, 2p6, that is 10 electrons. Then we got 3s2, 3p6, 4s2, it's another 10 electrons. Then we got 10 from the d orbital, and then 6 from p and 2 from 5s, so that's 18. So right now we're at 38. We got a long way to go. Okay, what's after 5s? Next is 4d, so that's 10, and 5p, 6, and then 6s2. So now we've got another 18. Takes us to 56. Okay, getting closer. So I definitely needed all of these. All right, what's next? So 4f. 4f gets 14 electrons. So that puts us at 70. So now we need 18 more. All right, 5d, 10. Now we're at 80. And we need 8 more. So 6p, 6. Now we're at 86. We need 2 more. 7s2. Perfect. We went through all of those. So as you can see, this is why we want to write things in noble gas notation, so that we don't have to use all of this space to write up our electron configuration. All of this is our electron configuration. So if we want to write it in noble gas notation, we're going to look for the last filled p orbital, because all of our noble gases end with the p orbital. As we'll see later today, we'll get a little trick there. So our last filled p orbital is 6p6. So radium is in period 7, so we need the noble gas that comes before radium, which I'm going to cheat. Radium is down here. So our last noble gas was radon. Okay, so if we want to write it in noble gas notation, radium is just going to be radon, which is Rn, 7s2. That is our noble gas notation for radium. Much simpler than this. But we need to know how to do that to get to here. Now that we understand it, we can use our shortcuts. Okay, let's keep going. All right, all of the elements in a group, remember what group means, it's a column on the periodic table. All of the elements in a group have the same number of valence electrons and the same valence electron configuration. So the valence electron configuration is whatever comes after that noble gas core. Okay, so for example, group 1 elements, which are called alkali metals, if you remember our family names, have 1 valence electron, and their electron configuration can be written as the noble gas with NS1 afterwards, where N is the period. So lithium is in period 2, so we write it as helium, 2s1. Sodium is in period 3, and then we got 4, 5, 6. So we've got, and then 7 down there at the bottom. I ran out of room. So sodium, we've got neon, 3s1. Potassium, which is K, we've got argon, 4s1. Rubidium, Rb, we've got krypton, 5s1. And cesium, we've got xenon, 6s1. And francium, radon, 7s1. And then here is our radium that we just did in our practice problem. So these are group 2, and group 2 works the same way as group 1, except now we have 2 valence electrons. So the number of valence electrons in the case of group 1 and 2, don't think this is not always the case, but in the case of group 1 and 2, that is the number of valence electrons. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. So group 1 we write as NS1. Group 2 we write as NS2. Okay, cool. All right, and then this beautiful periodic table here, this figure from your textbook shows the valence electron configuration of all the elements in the periodic table. So if we wanted to look at silver, for example, silver's electron configuration would be written as krypton, because we look at the previous noble gas, which is krypton, and then 4d10, 5s1. Okay, so this is the valence electron configuration, 4d10, 5s1. And you might be thinking, that's a little weird. We thought that right here at the end of the transition metal block was the D10 scenario, and that if it's, you know, past here, it should be 5s2, right? Well, silver is one of our exceptions to the typical electron configuration, as we'll see in a couple slides here. So there are some exceptions. Chromium is 1, copper is 1, silver is 1, molybdenum is 1. So basically, these guys might be exceptions. Don't want to give anything away, but those spots on the periodic table, since they're in the same group, if one of them is an exception and they should all have the same electron configuration, or valence electron configuration, I should say, they're probably all exceptions. Okay, cool. So let's keep going. So I should note that for elements past argon, the number of valence electrons is not necessarily equal to the number of electrons outside the noble gas core. So let's go back and look at these. So let's look at an example here. So for example, I use bromine as my example on the next page. So bromine over here is its valence electrons, its valence electron configuration. So after we put argon, would be the previous noble gas. After argon, we've got 3d10, 4s2, 4p5. It's a little hard to read, but that's what it says. So there's 17 electrons here, which corresponds with the group number 17, but we don't count all of those as valence electrons. The number of valence electrons comes from the outermost shell. So bromine has an electron configuration of this, make it a little easier for you to read, but it has 7 valence electrons, just like chlorine and fluorine. So if you look at chlorine and fluorine, they just have the s2p5 electrons because they aren't past the d electrons yet. Bromine is, but it still only has 7 valence electrons, which is what we would like to see because bromine is a halogen, just like chlorine and fluorine, so it should have a similar number of valence electrons because the number of valence electrons determines the chemical reactivity of the elements. And all of our halogens are in a family together, so they should have similar chemical reactivities, and they do because they have 7 valence electrons, even though bromine has these extra d electrons. We only count the electrons in the outermost shell. So when I say shell, remember that's the N. N is the whole shell. So the N equals 4 shell, the 4s and 4p orbitals is the outermost shell in bromine. So only 2 4s electrons and 5 4p electrons count as its valence electrons. Okay, cool. That's very important to remember for when we talk about bonding. So not super important right now, but I want you to try to remember it. It's based on this outermost shell. Okay, and then your book gives us this little graphic that shows us the different parts of the periodic table. So over here on the left, we've got what we call the S block. All of those valence electron configurations end with S1 or S2, and we call it the S block. Over here, we've got the P block. All of those valence electron configurations end with, they've got like an S2, P5, S2, P6. So it's this P, it ends in P, so we call it the P block. All right, the blue area here, our transition metals, as we like to say, are the D block. So our D block is anything that's going to, its valence electron configuration is going to end in D. So we've got D10 or D5. Anything that ends with the D electrons is going to be in the D block. And then finally, we've also got this wonderful little F block that we're not going to talk about too much in general chemistry, but you should know that the F block is all of the, we call them rare earth elements. The top row of the F block, those are the lanthanides. And the bottom row, those are the actinides, just what we call them. And we don't ever have enough room on a periodic table, like on a plain sheet of paper, to be able to read the periodic table if we write out our periodic table the way that it really should be written. But if we did, then you would see that the F block actually inserts itself here on the periodic table, just like the D block inserted itself between S and P. The F block inserts itself between S and D, which would make the periodic table really long and hard to read on a single piece of paper. So we don't do that. We like make it come down like this, but that really kind of obscures how the different properties are related, which might not make a lot of sense to you right now, but it will if you continue on in chemistry classes, as well as it makes it easier to write the electron configuration, because we can write our electron configurations just by going straight across the periodic table here. So once we hit 4s, then we're going to run into 3d after we hit 4s. Then we hit 5s, 4d, 5p, and after 6s is when we're going to run into the F block. So I'm going to go back a few slides and show you what I mean. So remember when I wrote out this electron configuration for radium? We went 4d, 5p, 6s, and then after 6s, we hit the 4f orbital. And that's exactly what happens here. We hit 6s, and then the 4f orbital. So if we write the periodic table out like this, it's easier to remember how to read. Just left to right, top to bottom, writing our electron configuration using the periodic table. Super cool, super easy, makes it a shortcut. You don't have to remember the energy levels anymore because they're already laid out on the periodic table for you. In this way, you just have to remember to go left to right, top to bottom. And that's basically it for writing electron configurations using the periodic table. it's important to know how we got here. It's important to know why the energy levels are arranged the way they are, which is why we started with that. But this is like our shortcut. This is how you will probably be writing your electron configurations in the future using the periodic table, because it's very straightforward, just like reading a book. And it might take some practice for you to get comfortable with it to that point. It might not be that easy to start with, but you will get it, I promise. What else was I going to say here? So these lanthanides and actinides, they insert themselves right here. If we look at the elements on the periodic table and not just a empty graphical version of the periodic table, we've got lanthanum, which is the beginning of the lanthanides. So lanthanum, and then after that we get cerium and the rest of the lanthanides, which then jump back into here. So lanthanum, cerium, lanthanides, and then we get to this one, lutetium, something like that. And then we jump back in here to hafnium, go across, and then we're down to radium and actinium, which is where we start our actinides with thorium. And then after thorium, we're going to go through all of the actinides to lawrencium. And then after lawrencium, we hit this guy, which I don't remember what RF stands for. And you probably won't need to either, but I'm pretty sure it's in your book to continue the rest of the periodic table. So as of right now, we have discovered / synthesized elements all the way up to element 118. We have not yet found element 119, though I'm sure we will, because we keep finding or creating, really, new elements every so often. But 119 is really exciting, not just because it's chemistry 119, but element 119 would be really exciting because it would be the first electron in period 8. We don't have any electrons in period 8 yet. So that would be the first one discovered / created in period 8, which basically starts a whole new row. So the actinides are where we start seeing artificial or synthesized elements, ones that we can't really say we discovered as much as we created. And those start with americium. Let me get my pen working, sorry. Americium and curium. Curium named after Marie Curie. She did not discover it, but they named it after her because of her amazing influence on the field of chemistry and physics. So all of the ones after plutonium, so 95 through 118 so far, have been artificially synthesized in the lab. They've been created using nuclear chemistry, actually, so they've bombarded other elements with neutrons and protons, making them fuse together into bigger elements. So usually they take uranium or plutonium, which are pretty unstable to begin with, and they bombard them with neutrons and protons, and well, usually they bombard them with other elements, actually. So like I think barium is one that they use a lot. They bombard uranium or plutonium with barium to create new elements by fusing those nuclei together. Pretty cool, right? Anywho, that was probably a lot more information than you need to know, but the periodic table is so cool. So I thought I'd share some of that knowledge with you. Anyway, where were we? So there are some unique electron configurations for the D block and F block, as I briefly mentioned before. Two of those notable exceptions are chromium, Cr, and copper, Cu. And the reason that these are exceptions to our electron configuration rules is that they have half-filled D subshells, so, or full D subshells. So these half-filled or completely filled D subshells are actually more stable than if we filled in order. So, for example, vanadium is written as predicted. We've got 4s2, 3d3, and then manganese on the other side of chromium is 4s2, 3d5. But this 3d5 subshell is very stable when it's half filled. So stable that we promote one of the 4s electrons into the 3d subshell when we form chromium. So chromium has one more electron than vanadium, but instead of just putting it here and having the 4s orbital still filled, we move that 4s electron up as well so that we have these two half-filled orbitals. The 4s and the 3d orbitals are both half-filled, which actually ends up being more stable than having one of them filled and one of them, and well, having the 4s filled and the 3d with 4 electrons. That's not as stable as this. And that's probably based on the electron-electron repulsion. So electrons are negatively charged, and when we pair them up, they have to be opposite spins, which we've seen already when writing our electron configurations. So instead of pairing up the 4s electrons and having an empty d orbital in chromium, we have all 6 unpaired electrons in chromium, which is more stable. The same thing happens for copper, except we have a full 3d orbital instead of a half-filled 3d orbital, 3d subshell, sorry. So nickel, which comes before copper, has 2 unpaired electrons in its 3d subshell, and we could easily put another one over here and have 1 unpaired electron in the 3d subshell for copper, but having 1 unpaired electron in the 4s is actually more favorable than the 3d, because if we have this filled 3d orbital, then we are maximizing our filling of the orbitals, and only having 1 in the further away 4s orbital. Even though 4s is lower in energy, we have a more stable core when we fill up the 3d subshells instead of the 4s. Okay, so those are our exceptions, and that happens with all of the other elements in those groups as well. So like I mentioned before, chromium, molybdenum, tungsten, copper, silver, gold, those all have that exception. So when we get to tungsten and gold, we have a different exception where we fill the 4f orbital and we fill the 4f orbital and then have the wrong, I could be wrong about that. Tungsten might not be an exception. It's really hard to read, to be honest. But it looks like we've got 4F14, 5D4, and 4S2, or 6S2. So actually, I don't know if tungsten's an exception. Sorry about that. But gold, it looks like, is. So we have 4F14, 5D10, and 6S1. So the 6S1 is an exception. I think we see the same thing over here. But the only exceptions you guys need to remember are chromium and copper. You don't need to remember any of the further down elements, though your book does discuss them. So chromium and copper are exceptions because of their half-filled or fully filled 3D subshells. And then this is just a diagram your book gives you to note the different regions of the periodic table. So the S and P blocks combined, those elements are called main group elements, which that term might have appeared on other previous periodic tables I gave you. These blue ones are the transition metals. And your book actually distinguishes between group 12 elements and transition metals because the group 12 elements have full D subshells, which make them a little special. And then over here, this is still the P block, but these are the noble gases, and they are also a little unique because they have the full P subshell. And down here, we've got our lanthanides and actinides, green and pink, respectively. Cool. All right, so last thing we're going to talk about, we're going to do a practice. Write the electron configuration for lead and determine its number of valence electrons. So lead is Pb, like peanut butter. It's number 82 on the periodic table. And let's write its electron configuration. I'm going to go straight for the noble gas electron configuration. So let's see what noble gas comes before lead. Okay, so lead's here. And the noble gas before lead is xenon. Okay, so xenon, and then we're going to start period 6. Okay, so xenon. So then we've got 6s2. Let me read it straight from the periodic table for you. So xenon, this is the 6s2. Those are those two electrons. Then we're going to jump down to the lanthanides, because after 6s2 comes 4f. So we've got these 4f electrons. I'm just going to, they're elements, but I'm going to call them the electrons in that 4f block for now. So we've got 6s2. There's 14 electrons that can go into the 4f subshell. So 4f14. All right, after we get through 4f, we're going to be in the 5d. So this is 3d, 4d, 5d. We're in the 5d subshell, and we want to go all the way through there over to mercury, and that's going to be 5d10. So we got that whole subshell filled as well. And then finally, then finally lead has 2 electrons after the D subshell. So it has 2 6p electrons. So our electron configuration is xenon, 6s2, 4f14, 5d10, 6p2. But remember, we don't want all of this to count our valence electrons. We only want the outermost shell, which is 6 and equals 6. So lead has 4 valence electrons. Okay, awesome. So that is how you write an electron configuration using the periodic table. Let me, oops, show you this way maybe. So we went 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and then 6s, fp, 5d, and then 6p. Put us like right here for lead. Okay, just reading left to right, top to bottom to write our electron configuration using the periodic table. Okay, awesome. Thanks, guys. I'll see you tomorrow.